Tunnel builders worked in spaces so tight their shoulders brushed the walls, knowing a single crack above them could turn the entire ceiling into a killing blow. Air thinned without warning and left grown men gasping like they were drowning on dry ground. Some shifts felt so claustrophobic that even the steady ones fought rising panic. Yet they kept digging, never certain the next hour would be safe. What they endured remains one of the most overlooked risks in our history. If stories like this matter to you, consider subscribing to help preserve the lives and lessons of those who built the world beneath our feet. Now, let us step into their tunnels and understand why every shift felt like a gamble with fate. Tunnels have always been treated as feats of engineering, but for the people who carved them, they were reminders that the earth has moods of its own. Workers stepped into openings held together by timbers that strained against weight older than civilization. Every shift began with a quiet understanding that the mountain did not need a warning to change its mind. In the late 19th and early 20th centuries, tunnel construction surged as railroads, mines, and hydroelectric projects expanded across the world. Men and women were sent beneath the surface to create passages through granite, shale, and limestone that had never been touched by light. Those rocks were considered stable until they were disturbed, and once disturbed they behaved with a kind of unpredictable will. Most collapses began with sounds so soft they were easy to ignore. A faint tick of settling stone could be nothing, or it could be the first sign that pressure was travelling through the ceiling like a ripple in heavy cloth. Workers learned to read vibrations through their boots and judge danger by the way dust drifted after a blast. These small observations often meant survival, but even the best crews were sometimes fooled. Historical accounts from large projects like the Hoosac Tunnel in Massachusetts show how often crews faced collapses despite careful planning. In that era, geologic surveys were limited, and maps were based more on guesswork than science. Miners pressed forward relying on experience more than instrumentation, and experience was not always enough. Sections that looked solid during the morning inspection could shear apart by the afternoon. Timber supports helped but were rarely perfect. Wood swelled in damp shafts, warped under pressure, and snapped from internal stress that inspectors could not see. When one beam failed, the weight shifted instantly to the next, and the collapse spread like a chain reaction. Survivors often described the noise as a deep rolling groan followed by the sudden roar of stone collapsing into the void. Air quality made the danger worse. When ceilings sagged even slightly, dust filled the tunnel and turned each breath into a struggle. Fine particles coated the throat and robbed workers of the oxygen they needed to think clearly. Panic rose quickly in those moments, and many became disoriented in the haze as they tried to reach an exit that felt impossibly far away. Claustrophobia was an enemy that rarely made the written records, but shaped the emotional reality of everyone underground. Tight spaces pressed shoulders inward, and movement slowed to a crawl as crews squeezed through freshly blasted chambers. When ceilings dipped low, helmets scraped the rock and forced workers into a crouching shuffle that strained muscles and frayed nerves. Some said the weight of the earth felt physical, as if the mountain leaned down upon them. Yet despite all this, the work continued because the world above needed what the tunnels promised. Railways had to pass through mountains, cities required sewer systems, and nations demanded access to resources hidden far below the surface. The danger did not stop progress. It simply became part of the cost. Tunnel builders feared collapse, but many would tell you that the air itself was just as deadly. Underground spaces stole oxygen quietly, long before anyone realized something was wrong. What looked like ordinary stale air could shift into a lethal mixture that robbed men and women of breath faster than rising water. Black damp, a buildup of carbon dioxide, was one of the earliest dangers known in mining and tunnel construction. It settled in low pockets, invisible and odorless, and suffocated anyone who stepped into it. Lamps dimmed as oxygen levels fell, giving crews only a moment of warning before dizziness and paralysis set in. Those who ignored the signs rarely had a chance to retreat. Historical reports from coal and iron tunnels in Scotland, Pennsylvania, and Saxony describe entire crews collapsing within minutes when ventilation systems failed. Early engineers relied on natural drafts and crude fans powered by hand or mule-driven shafts. These systems were often disrupted by cave-ins, equipment failures, or simple miscalculations about airflow. Once black damp pooled, recovery teams had to crawl in with fresh air apparatus that weighed more than the stretchers used to carry out the victims. White damp presented a different but equally frightening threat. When carbon monoxide accumulated after blasting, it bonded to blood with ruthless efficiency. Workers who survived the initial explosion often fell unconscious moments later as the gas seeped through the chamber. In the early 1900s, safety inspectors documented rescue attempts where volunteers dragged co-workers over debris only to collapse themselves from a few breaths of the poison. Fire damp, a mixture of methane and air, added the constant horror of explosion. While more common in coal environments, fire damp appeared in hard rock tunnels where organic pockets had been sealed for centuries. A single spark from a pick or lamp could ignite the tunnel with devastating force. Newspapers from the period describe crews who refused to strike tools until the foreman declared the air tested, yet accidents still claim dozens each year. Ventilation failures also amplified the psychological strain that came with the work. When airflow slowed, the heat inside the tunnel often rose to unbearable levels. Walls dripped with condensation, and clothing clung to the skin as if glued in place. The combination of humidity and low oxygen created a feeling of suffocation, even in spaces that technically remained breathable. Many workers described moments when their instincts screamed that the tunnel was closing in, even when the structure remained stable. The arrival of mechanical fans in the early 20th century marked progress, but their reliability was far from perfect. Power outages, broken belts, and clogged ducts caused sudden drops in air quality that sent entire shifts scrambling toward the entrance. Rescue logs from major projects like the Simplon Tunnel and the early New York subway expansions show how often foremen ordered emergency evacuations because the fans hesitated or slowed. Despite these dangers, crews continued advancing day after day. They trusted the thin line of breathable air carried down through shafts and ducts, knowing it could vanish without warning. The work demanded courage that few outside the industry ever understood. Each breath underground was a reminder that the margin between life and death was measured in the air itself. Explosives gave tunnel builders the power to carve through mountains, but they also introduced a new kind of uncertainty. A charge that behaved perfectly on Monday could misfire, sputter, or detonate early on Tuesday. Workers understood that every blast involved trust, and trust underground was always conditional. In the 19th century, black powder was the primary explosive used to shatter rock. It burned rather than detonated, which meant its force was slower and less predictable. Moisture in the tunnel weakened the powder and altered burn rates, so crews often found themselves lighting fuses that behaved differently each time. Variations that seemed minor could shift the entire outcome of the blast. When dynamite arrived in the 1860s, it changed the industry but did not eliminate the danger. It was more powerful and more reliable, yet it also degraded when stored improperly. Nitroglycerin could seep out of sticks and form oily pools that were shock-sensitive, even to a dropped tool. Reports from early alpine tunnels describe workers handling bundles of dynamite with shaking hands, hoping the material had not turned volatile. Misfires were an unavoidable part of tunnel work. A fuse might extinguish in a damp borehole or burn slower than expected. Crews waited the required time before returning to check the face, but a delayed explosion could still occur the moment they approached. These incidents created some of the most feared situations underground. Anyone who stepped forward too soon risked triggering the blast with nothing more than their footsteps. Even when charges functioned as intended, fly rock remained a significant hazard. Shattered stone ricocheted through the tunnel with incredible force and little control. Protective barricades reduced the danger but never removed it. Injuries from fragments were so common during the construction of the early US. Railroad tunnels that foremen kept medical supplies near the blast sites at all times. Early blasting caps introduced another layer of complexity. They relied on mercury fulminate, which was sensitive to shock and temperature. Caps stored in heat could fail entirely, while colder conditions made them unpredictable. Workers handled them carefully, often carrying them in padded cases to prevent accidental strikes. Despite these precautions, explosions caused by faulty caps appeared frequently in accident records. Fuse timing created its own risks. Before electric detonation systems became standard, crews used cut lengths of fuse that burned at inconsistent speeds. A worker might light 6 holes believing he had 30 seconds to retreat, only to discover the fuses were burning faster that day. Some crews learned to walk backward immediately after ignition, facing the blast site so they could spot any abnormal flare or sputter. Even electric blasting did not remove all uncertainty. Moisture could short the wires or influence the resistance, causing only part of a charge to fire. Partial explosions left the rock weakened and unstable, which set the stage for collapses when the crew returned to clear debris. Historical accounts from the Cascade Tunnel and the Mont Cenis project reveal how often these unstable faces led to secondary disasters. Despite the risks, blasting was the only way to advance through the Earth at the speed modern nations demanded. Workers accepted the danger because progress required it. They lit the fuses, stepped back, and trusted that the mountain would give way rather than take another life in return. Tunnel builders trusted their lives to supports that were never as strong as they appeared. Timber frames stood between crews and hundreds of tons of overburden. Yet even the best beams weakened in ways the eye could not detect. Underground, time, pressure, and moisture conspired against the materials meant to protect the people below. Timbering was the earliest method of reinforcing tunnels, and it remained common well into the 20th century. Freshly cut wood seemed strong at the surface, but in the humid, mineral-laden air of a tunnel it changed quickly. Fibers swelled, warped, and rotted, sometimes within weeks. A beam that looked solid could be hollowed by decay, waiting to snap under the slightest shift of rock. When supports failed, they often did so with little warning. Workers described hearing a faint pop or crack that signaled internal stress giving way. The sound travelled through the tunnel like a warning from the earth itself. In many cases, the collapse followed only seconds later, leaving almost no time to run. Rescue reports from early Pennsylvania coal drives and Cornish tin mines document countless cases where crews were caught beneath the sudden release of weight that had been building for days. Steel arches and ribs were introduced to solve these problems, but they brought challenges of their own. Metal supports resisted rot but were vulnerable to corrosion, bending and buckling. The enormous pressure exerted by rock layers could twist steel into distorted shapes, compromising entire sections. During the construction of the Butte copper tunnels in Montana, engineers noted that steel ribs often deformed overnight, squeezing inward as if clamped by invisible hands. Geology determined whether supports held or failed, yet geology was rarely understood in detail during early projects. Tunnels were driven through layered strata that shifted differently under stress. Sedimentary rock might crumble gradually, while granite could fracture violently. Crews could brace one section perfectly and find the next section collapsing despite identical preparations. Reports from the Simplon Tunnel reveal that crews encountered zones where rock behaved almost like wet sand, swallowing supports as soon as they were placed. Moisture intensified the uncertainty. Water seeped through cracks, washing away fines that helped hold the ceiling together. Timber frames softened in the dampen and steel corroded faster than expected. In deep tunnels, warm air met cooler rock and formed condensation that dripped constantly, turning floors into slick surfaces and weakening everything it touched. Some workers said the drip never stopped, as if the mountain itself was leaking from the strain. Pressure bumps created another danger. As rock compressed and released stress, entire sections could heave upward or inward. A pressure bump could shatter supports instantly, filling the tunnel with debris. These incidents were recorded frequently in coal seams across West Virginia and Wales, where the natural weight of the earth changed unpredictably as voids expanded. Even well-built supports could not overcome human error. Crews working under tight deadlines sometimes spaced frames too far apart or used timber of inconsistent quality. Inspectors noted areas where bracing was rushed, especially in boom years when railroads demanded rapid progress. The tragic collapses in the early New York subway system highlighted how minor oversights accumulated into catastrophic failures. Despite every risk, tunnel builders returned to the confined spaces day after day. They trusted the beams above them because trust was the only way the work could continue. Each support held back the mountain for one more shift, but no one underground ever forgot that the balance could shift without mercy. Water was one of the oldest enemies of tunnel builders, and it behaved with a patience that made it especially dangerous. It seeped through microscopic cracks, gathered in hidden pockets, and waited for the moment when pressure gave it a path. What began as a trickle could transform into a catastrophic flood that, erased entire crews before they understood what had happened. In many early tunnels, no one understood how much water the surrounding rock held. Mountains acted like reservoirs, storing rainfall and snowmelt deep within fractures that had formed over centuries. Once the tunnel face approached these pockets, the first sign of danger might be a sudden breeze of cold air. Moments later, water exploded through the rock with the force of a bursting dam. Historical records from the construction of the Severn Tunnel in the 1870s show how immense these inrushes could be. A vast underground river was discovered unexpectedly, and it overwhelmed pumps, filled shafts, and trapped workers in rising black water. Diaries from the period describe crews clinging to braces as the flood swept past them, knowing that those caught upstream never stood a chance. It took years of effort and some of the largest pumping systems of the era to tame the flow. Smaller tunnels faced the same danger on a lesser scale. Groundwater seeped constantly into many shafts, pooling in low areas and turning floors into treacherous paths. Timber supports softened as water soaked into the grain, and clay layers swelled until they pushed against the tunnel walls. Crews worked ankle-deep in mud that threatened to swallow tools and twist legs. Even when water levels were low, the constant damp weakened every structure underground. Water did more than flood. It also carried dissolved minerals that hardened into deposits on equipment, hoses and ventilation pipes. Pumps clogged with silt and needed constant cleaning. If a pump failed for even a short time, water levels rose with alarming speed. Foremen often kept backup pumps running at all times because they knew that once the water gained ground, it was nearly impossible to reverse its advance. Temperature changes added another layer of risk. In winter months, cold air entering the shafts caused condensation to freeze along walls and ceilings. Ice expanded within tiny cracks, prying apart rock until entire slabs fell without warning. Workers described hearing sharp cracks like distant gunfire as ice worked its way through the stone. Thawing made conditions even more unpredictable, sending sudden gushes of water into the already unstable tunnels. Water also threatened the chemical integrity of explosives. Moisture seeped into drilled holes, weakening powder charges and causing misfires that left crews guessing what remained active. Wet fuses burned unevenly or extinguished before reaching the charge. Many blasting accidents were traced back to waterlogged materials that behaved in ways no one could anticipate. Some of the most tragic incidents occurred when water eroded the floor beneath tracks and equipment. Heavy carts sank into softened ground, trapping workers behind them. Rescue teams struggled to move machinery bogged down in thick slurry, and delays often cost precious minutes during emergencies. Despite all of this, tunnel builders learned to work with the water rather than against it. They installed drainage channels, built sumps, and ran pumps day and night. But no system was perfect. Water seeped, pooled, froze, and flowed in ways that reminded every worker that the ground above and below them was always shifting. The machines used to carve tunnels were supposed to bring progress, yet they often introduced dangers that rivaled the natural threats underground. Compressed air drills, steam engines, locomotives, and haulage systems filled the tunnels with power that did not always stay under control. When machinery failed below the surface, the consequences were immediate and unforgiving. Pneumatic drills were among the first tools to transform tunneling work. They drove steel into rock at speeds no human could match, but they generated intense vibration that weakened surrounding stone. The constant pounding loosened fragments overhead, leaving workers exposed to sudden falls even in areas that inspectors considered safe. The noise of the drills made it impossible to hear approaching trouble, which robbed crews of their earliest warnings. Steam engines created another set of hazards. Boilers operated in tightly confined spaces, surrounded by flammable oils, dry timber, and workers who had little room to escape if anything went wrong. A boiler rupture underground was far more dangerous than one on the surface because the blast had nowhere to disperse. Accidents in early British railway tunnels recorded cases where steam filled chambers so quickly that workers collapsed from heat before they could take a single step towards safety. Compressed air systems powered much of the underground machinery and ventilation, yet they were vulnerable to sudden pressure failures. A burst air hose could whip through a tunnel with tremendous force, striking anyone nearby with the impact of a battering ram. Air receivers occasionally ruptured from fatigue or corrosion, sending metal fragments through the darkness at lethal speeds. Rescue journals from the late 1800s describe how teams found hoses wrapped around beams and tools, evidence of violent failures that happened in seconds. Haulage locomotives, introduced to move rock more efficiently, created risks few crews expected. Their exhaust filled low tunnels with fumes that accumulated faster than the ventilation could remove them. Workers often tied cloth over their mouths to filter the smoke, but it offered little protection. A single stalled locomotive could turn a stretch of the tunnel into a suffocating trap before supervisors realized what had happened. Cables and winches used to raise and lower equipment also produced frequent accidents. If a cable snapped under load, the recoil tore through the shaft with enormous force. Crews learned never to stand directly beneath a hoisted object, yet the cramped conditions often left them with no choice. In some documented cases from Austrian hydro tunnels, broken cables cut through timbers and stone as if slicing through cloth. Lighting systems introduced their own complications. Early tunnels relied on open flames and oil lamps that flickered unpredictably. Even when electric lighting became available, it was unreliable underground. Short circuits plunged entire sections into sudden darkness, leaving dozens of workers disoriented while machinery continued to run around them. Some lost their footing in the confusion and fell into excavation pits or between moving carts. Mechanical ventilation fans, though essential, sometimes malfunctioned in ways that created panic. A sudden shutdown left crews unsure whether the failure was electrical or caused by a deeper problem. The uncertainty sent workers rushing toward exits, crowding narrow passageways not designed for quick evacuation. Reports from the Musser mine tunnels note instances where panic itself caused more injuries than the original malfunction. Every piece of machinery underground represented a mix of progress and risk. The tools made the work faster, but they also added threats that demanded constant vigilance. Tunnel builders lived with the knowledge that the machines designed to help them could turn into hazards the moment a bolt slipped or a valve stuck. It was another reminder that nothing below the surface ever behaved exactly as expected. Tunnel building demanded physical strength, but the greater test was endurance. Workers laboured in conditions that slowly eroded their bodies and minds, turning each shift into a trial that few outsiders ever understood. The constant strain created vulnerabilities that made accidents far more likely, even when the tunnel itself remained stable. Long hours were the foundation of the problem. Crews often worked 10 to 12-hour shifts, sometimes longer when deadlines tightened or unexpected problems halted progress. The repetitive motions of drilling, carrying timbers, clearing debris, and setting equipment wore down the muscles that kept balance and coordination intact. By the final hours of a shift, workers moved more slowly, reacted more slowly, and made decisions through a haze of fatigue. Heat added another layer of difficulty. As tunnels grew deeper, temperatures often rose dramatically due to geothermal gradients. Miners in South African gold tunnels recorded temperatures so high that wet clothing dried within minutes of stepping into deeper galleries. Even in temperate climates, shallow tunnels trapped heat from machinery and human bodies, creating environments where sweat poured constantly and dehydration set in with alarming speed. Under these conditions, fainting spells were not uncommon. Dehydration also clouded judgment. Medical reports from large late 19th century projects noted how many injuries occurred during periods of intense heat because workers misjudged distances or lost their footing on uneven ground. These mistakes seemed small on the surface but became deadly underground, where a stumble near moving carts or an open excavation pit could change the outcome of a day in an instant. Cold worked with equal force in other regions. In subalpine and northern climates, tunnel work exposed crews to temperatures that stiffened joints and slowed reflexes. Tools became painful to grip, and metal surfaces drew heat from unprotected hands. Workers had to strike rock with precision, but cold made fingers clumsy and increased the risk of accidents involving hammers, chisels, or drill steels. Historical records from Scandinavian mining tunnels describe entire shifts where workers battled numbness long before facing any geological threat. Noise contributed to the breakdown of endurance as well. The constant hammering of drills, scraping of metal, rumbling of carts, and shouts of co-workers created a sensory overload that persisted for hours. Over time, the noise produced a dull exhaustion that made concentration difficult. Workers described feeling as if the sound pressed down on them, draining their focus until even simple tasks required deliberate effort. Physical strain was compounded by irregular access to rest. Emergency repairs, blasting cycles, and water control often forced crews to remain underground long after they expected to leave. Sleep schedules were disrupted constantly. Fatigue accumulated not over days, but over weeks and months. Researchers studying historical tunnel projects later concluded that exhaustion contributed to a large percentage of accidents that were once blamed solely on environmental factors. Food and nutrition played their part as well. Tunnels lacked proper eating areas, and meals were often taken quickly in cramped spaces with little light. Workers relied on whatever provisions they carried, which did not always meet the needs of such intense labour. Inadequate nutrition made them more susceptible to illness and slower to recover from minor injuries. Even small infections spread quickly in the damp conditions. Endurance also had a psychological dimension. The confinement, monotony, and pressure of the environment created a level of tension that mounted as the shift progressed. By the end of a long day, nerves were often frayed, and small disagreements could escalate as patience thinned. This stress made teamwork more difficult and amplified the dangers of working in close quarters. In the end, endurance became its own hazard. The human body was forced to operate at the edge of its limits, shift after shift. Workers learned to push through fatigue because the job required it, but deep down they knew that exhaustion made every danger below the surface more likely to strike. Many of the dangers underground began with choices made far from the work site. Engineers, contractors, and financiers shaped the conditions that crews faced, and their decisions often determined whether a tunnel would be safe or perilous. Errors made in offices and boardrooms travelled downward until they became hazards that workers could not see coming. Planning errors were among the most overlooked causes of tunnel disasters. Early surveys relied on compass readings, surface observations, and incomplete geological maps. Engineers approximated the makeup of the rock and the depth of water-bearing layers, but these estimates were often based on limited data. When the tunnel face finally reached those predicted zones, the reality frequently proved harsher than expected. Some projects encountered rock formations that crumbled like ash instead of holding firm, forcing workers into emergency reinforcement long before the project was ready. Financial pressures had a similar impact. Contractors accepted tight bids to win government or industry contracts, then pushed crews to maintain impossible schedules. Any delay risked penalties that could erase profits, so supervisors advanced the work even when conditions suggested caution. Records from the construction of several early American railroad tunnels show foremen ordering excavation to continue through unstable ground rather than waiting for reinforcements, a choice that cost lives when the earth shifted unexpectedly. Material substitutions contributed to further risks. When budgets tightened, companies sometimes supplied timbers or steel of lower grade than originally specified. Workers received the materials assuming they met the required standards, only to watch them deform, split, or corrode long before they should have. Investigations into collapses from Italian railway projects in the late 1800s documented entire sections where substandard supports were traced directly to procurement shortcuts. Decision-makers also underestimated the effects of groundwater. Some planned routes passed directly through aquifers or soft strata that were poorly understood at the time. Instead of rerouting, officials pressed ahead to avoid delays. This led to constant flooding, rapid deterioration of equipment, and working conditions that hovered at the edge of disaster. Crews had to compensate with improvised drainage and round-the-clock pumping, even though these measures could never fully match the water's force. Ventilation planning suffered similar oversights. Engineers calculated airflow based on theoretical conditions rather than actual underground realities. Once blasting commenced and machinery filled the tunnels with heat and dust, these systems became inadequate. Some tunnels relied on shafts spaced too far apart, forcing workers to labour in stagnant air that grew heavier by the hour. Reports from the London Tube extensions in the early 20th century reveal how planners underestimated the amount of fresh air required, leaving crews to struggle through stretches of stale, humid atmosphere. Communication failures also contributed to the danger. Information about unexpected ground behaviour, new faults or water pressures did not always move quickly between shifts. Workers sometimes entered a section assuming it was stable because no one had told them about the signs of movement discovered the previous day. This lack of updated knowledge left crews vulnerable to hazards they believed had already been addressed. The most tragic part of these failures was how preventable many of them were. Better surveys, more accurate budgeting, and clearer communication could have spared countless workers from unnecessary risk. Yet the drive to complete tunnels quickly and economically often overshadowed caution, creating situations where the decisions made above ground set the stage for disaster below. When disaster struck underground, the difference between life and death often depended on the bravery of the rescue crews. They entered tunnels that others were fleeing, carrying only the tools they could manage and the hope that someone was still alive inside. Every rescue effort revealed how much danger remained even after the initial collapse or failure. The first challenge was simply reaching the trapped workers. Debris blocked the entrances, and the air beyond often held unknown levels of toxic gases. Rescue teams moved slowly, crawling over shattered timbers and twisted steel, pausing often to listen for shifting stone. Any wrong step could trigger another fall. The work demanded careful precision at a moment when instinct urged them to rush. Visibility was another obstacle. Dust hung thick in the air after a collapse, turning lantern light into a pale glow that barely illuminated the ground. In the earliest days, rescuers relied on hand-carried lamps that flickered in the moving air. Later crews used battery-powered lights, yet even these struggled to cut through the haze. Moving forward required feeling along the walls, unsure what lay ahead. Breathing equipment was rudimentary at first. Early rescue teams used simple cloth filters or canisters that provided limited protection. These devices worked only briefly, and rescuers often had to turn back before reaching those they hoped to save. Historical accounts from European coal tunnels describe how rescuers emerged gasping, faces streaked with soot, driven back by fumes that settled in pockets from one chamber to the next. Heat added another danger. After a collapse or explosion, fires sometimes burned deep within the rock. The tunnel turned into an oven, where temperatures rose quickly and limited how long rescuers could remain inside. Teams soaked their clothing in water before entering, hoping to buy a few extra minutes. Even so, burns and heat exhaustion were common. Many rescuers required medical care long before the victims were reached. Noise, or the lack of it, played a haunting role. Tunnels held silence deeply. Rescuers tapped on the walls, struck rails with hammers, and shouted names, hoping to hear a faint reply. In rare moments, a single knock or muffled cry guided them forward. More often, there was nothing but the shifting groan of stone that reminded them how unstable the tunnel remained. Some rescues required digging new passages to bypass collapsed sections. Crews shifted tons of debris by hand, loading rubble into carts and carrying beams into cramped areas to brace the ceiling. Progress was painfully slow. Diaries from the north of England's deep mining disasters describe men working for days with almost no sleep, kept moving only by the possibility that someone inside was holding on. The emotional toll was immense. Rescuers knew many of the trapped workers personally. They had shared meals, jokes, and long shifts with them. That familiarity created a weight that pressed harder with every hour of uncertainty. When victims were finally reached, the relief was often overshadowed by the brutal reality of what they had endured. Despite all the hardship, rescue crews continued because the alternative was unthinkable. Their courage did not erase the dangers underground, but it offered a final chance for life where hope seemed impossible. These rescues revealed not only the risks of tunnel work, but also the remarkable determination of those who refused to leave their fellow workers behind. For all the dangers beneath the surface, tunnel builders kept coming back. They walked into shafts scarred by previous failures and picked up the tools that had taken lives only weeks before. Their willingness to return reflected a mixture of necessity, pride, and a sense of purpose that grew stronger each time they stood at the mouth of a new tunnel. Economic reality played a powerful role. Many workers came from families that depended on steady wages, and tunneling paid better than most surface jobs. The promise of reliable income outweighed the fear of disaster. In communities from Wales to the American West, men with few alternatives accepted the risk because the work kept food on the table. For them, the choice was not between danger and safety, but between danger and hardship. But money alone did not explain their commitment. Tunnel work demanded skill, and that skill created identity. Crews developed a deep respect for the craft. knowing that each strike of the drill and each set of supports represented experience earned the hard way. They took pride in building something permanent, something that altered landscapes and connected cities. Even decades later, many spoke of tunnels they helped construct as if they were monuments carved into the earth. Camaraderie also played a central role. Teams worked in close quarters where cooperation was more than a virtue, it was a survival tool. They learned each other's habits, strengths, and weaknesses until the group functioned with an almost instinctive unity. When someone was in danger, others moved without hesitation. The bonds formed underground lasted long after projects ended, linking workers in a shared history that few outside their world could understand. Trust in the foremen and engineers mattered as well. While mistakes were made, many leaders earned the respect of their crews by insisting on safety measures and refusing to cut corners when lives were at stake. Workers followed them from project to project because they knew leadership could mean the difference between a routine shift and tragedy. Oral histories record cases where entire crews refused employment unless certain foremen supervised the job. Another reason they returned was resilience built over years of exposure to hardship. Tunnel builders were accustomed to environments that tested endurance and courage. They learned to adapt quickly to changing conditions and to stay calm when others might panic. This resilience became a source of confidence that helped them face each day despite the risks. There was also a sense of purpose that came from seeing how tunnels transformed the surface world. When a railway emerged from a mountain or a water system carried its first flow, the workers understood that they had created something that would serve generations. Their labour connected distant regions, powered growing cities, and made modern life possible. The knowledge that their work shaped the future provided motivation that fear could not extinguish. In the end, tunnel builders returned because the work was woven into their lives. They understood the risks more clearly than anyone, yet they also understood the value of what they were creating. Each shift carried uncertainty, but each completed tunnel carried proof that their efforts mattered. They accepted the danger because the world needed passages carved through stone, and someone had to build them.